Let's see if I got lag in that. Crazy. It's like every so often let's start OBS and stream and it just got a weird circle. I guess it's going. Looks okay. I was just gonna play the game for a little bit, stream just because. What's up? Thing after another is being weird. That's one. Time and days gone up there. That's all normal. Didn't take anything out. Oh well, I'm not messing with it. Let's try. Don't care. I'm not getting no GPS navigation. What? There's nothing. Nothing on where I'm going. Nothing on the job. All I do is hit pause. Oh well. We'll make it. Only 2,800 miles or something like that. I don't know now. Does it even show the job? Yeah. Oh well. I'm restarting the game because I don't understand why I had navigation. No, I don't have navigation. That's crazy. Because it's coast to coast. I mean, it was on there a second ago. Whatever. Truckee decided it's not going to work either. I'll restart that. Restart the dumb game. I'll put that plug in back. back in or what? Still nothing. And no navigation. But my exterior, I'm not messing with it. There's something cursed about this. We done with that. No, thank you. I'll pass. 100% I'll do something different. Oh yeah, I'm not gonna be able to go there. Why? Because the teleported somewhere and it ate my trailer. Destroyed the truck. Look at that. It just destroyed it. Hooked up my trailer. And I'm getting rid of it anyway. It's already a curse. Be down. I'll just leave it. I don't care. That's all right. No, this is doing. Just one thing after another wants to be ugly. I was just doing that. Oh. Can't take that. That's it. That's normal. Nothing to change. Didn't change nothing. Thank you something. Well. Yeah, it's supposed to show. Okay. Go ahead. Close. Oh, they should make a movie about this. What's this game called? Loading Screen. That's what this game is called. That's all this game does is loading screen. All that just to get a simple plug-in working. Okay, whatever. Go find something. Not messing no more. Okay. Yep. See, everything's back to. I got it on video where I already repaired this truck. You can hit save all you want. It don't save. And that was somewhere else too. Yep, I was supposed to be over here. I was just trying to drive across the country. That's all I wanted to do. That's all. Get the park brakes off. Tired of looking at it. No, man, the trailer got me. That was disconnected too. Let's try this again. POS. Pay nothing. It's shorter now. Dang it. That one won't work. Because it doesn't read. It doesn't read Mexico. Man. It's just almost like a trailer. It's just no. That's it. Well, this place is terrible. I'm never gonna drive. Like, ever. Not today at all. I'm gonna misclick everything. Next job I get, it'll probably be like a 20-minute trip just to get to it. Oh, where are we going? Yeah, that's pretty good. Wonder if dispatch will pick it up. I'll test it. Did it actually? I don't even think it. I don't think it took it. Did it? It didn't. I guess it did. It's not setting the GPS. Is this plugin messing the GPS up? More Jesus. To nowhere. Nowhereville. Oh, 'cause it's here, huh? Yeah, I should have known that. Oh, it's near. See if I get a job. Nope. Not doing it because I wanted to register on the ATS Dispatch Pro site. So if it's not going to fill in jobs, I'm not going to do it. Man, I just can't find. No, I'm not even on the board now. What in the world? Where am I? I'm invisible? No, that won't work. Be a cool one. Just gotta stay within SCS. Oh well, forget it. Do this. Pepper, come on, man. Stop, 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 stop. Kid trying to steal a mouse. We're going Target. Should work. Should work. Okay. Yeah, it gave me jobs too. General mails, bills, negative. Oh, I forgot. Nice, cheesy. I guess not until somewhere down the road. Oh boy, there's no telling where it could be. I'll just wait till it prompts me. Don't worry about it. Alright, how do I make this bad boy play? Just Forgot the button I wanted to push. Okay. But we're in single player. I could do that. I forgot. Mother trucker. Right. Uh-oh. Busted. Damn. It's picking it up. Oops. Seeing that the video was actually playing, or the sound was playing through the OBS from the dashboard. It's not that. So
That loop that you made with the chain, you put it in the loop.
Brian coaches Junior through the hookup.
Excellent.
And I'll put it in like right here, right?
Yep.
I'm learning which points I should be hooking up to, but to always be cautious too.
And then,
Like that?
yep. And then hook this big ugly hook through the loop you just made.
Okay. Oh, like before.
Yep, exactly like before.
Junior's doing pretty good. He's picking it up.
Top side.
I got 250 feet of winch line on this truck, and the drum is bare. Okay, good to go.
The heavies line up for the
I think I
ball.
figured out some. Maybe hooked.
With two single lines from the horns. And a double line from HR 130. They'll try to roll the flatbed and coax it up the bank.
Once Jamie starts pulling, then the truck will actually invert itself back onto its wheels.
The narrow road will be closed until the recovery is done.
We don't have much room to work with on logging.
We're committed now, so traffic is what it is.
I'm absolutely amazed at how many people
I really can't see it that good. It'll wash it out. It'll make it brighter. I wonder if this will help.
On Jamie's vintage record,
The handles down.
today,
Push the bolt down.
Brandon is on the controls.
Never actually operated one of Jamie's classic tow trucks before, but I'm always willing to take on new chances and opportunities.
Dad, I was the one that hooked it all up. Dad, just to make you more nervous.
Via remote control, Jamie will operate the Pete.
Gonna start coming now, Brandon.
Okay, we got some action happening, I'm thinking.
But the pickup still attached to the deck is a wild moment.
We've got a really tricky situation here. If the pickup comes off,
I could.
That's on.
Oh no. I'm a crash.
In the freezer,
I'm a crash. God damn it. No, no, no.
keep going, Jamie.
Jamie is in front of
No, I really didn't want to do that.
after a crash involving his own.
It constantly sucks if you can't control your vehicle in console.
These trucks have the shit.
Discord, almost anything,
Jamie breaks
man.
his modern record and keeps an eye on the casualty log. Under Jamie's direction,
See how you load up, then I give you a little hand?
Brandon operates 47-year-old.
This is the first time that Brandon and I actually worked together. He's running a truck, and I'm running a truck.
I love it.
He's probably a little nervous, but he's getting it.
Here she comes.
Well, it's going up pretty good, eh?
But winching the flat deck of the rough bay
Put his face on his truck and start to shift.
is testing Jamie's reverse drop side.
Yeah, there's quite a few good sized logs there in your roll up. I'm pretty sure we're gonna get about half of them.
Feels like there's so much resistance here.
They're off the ground, Jamie. They're off the ground up here.
The thing's halfway up the mountain. I can't let it go.
That's a lot of pull.
And the Pete's wheels
Jamie!
aren't the biggest problem.
Jamie! On the boat.
The strain could be too much for one.
Looking at this map here, it looks like it's starting to.
Keep that hose stops till the hands, you guys. Keep pulling that. It's bending over. It's gonna break. More.
A little bit of fracture. Oh no, they didn't take the stress.
I'm between a rock and a hard place. Oh my god.
Miles away, high on the cove. The first dump of snow in months has hit the mountain pass. Highway maintenance supervisor Curtis Brown monitors the situation.
Pretty much all hands on deck. Doing our best to keep it open.
South of the snow shed. Authorities make sure transport drivers chain up for the steep climb.
The trucks that decide to go by without having chains on, that's what we're down there to enforce.
Attention, GPS.
But when trouble still strikes, the last line of defense is Team Green.
First time I come up on the hill every year, I feel
Somewhere.
great.
Got my dancing shoes on.
Towing scoreboard has been called for a semi and spun out despite training up.
This guy, for whatever reason, has too many chains apart.
So Gord's job
You gonna jump in before this thing? No, too late.
that truck disappear?
Jamie's on the scroll back around.
If that boom snaps, it's coming right at you guys.
He's under some hairspray. Recovering one of Jamie's old trucks.
That's all audible.
I'm really worried right now. This thing could snap off. Anything online? It's gonna break.
We can't drop the wall. It's still suspended there halfway up the mountain.
But Bones moved.
It's broken,
This is
Mo.
the fight.
Didn't take the stress.
I actually pushed it against the wall, so it bent the boom on way more. You know, sometimes there's collateral damage in these jobs, and this is one of those times. I'm gonna run this one only.
But Jamie marches forward.
Hold that side.
Yeah, you can go do it on that side. Come Ryan.
Yeah.
What we gotta do now is get a line down the bottom
purchased a military truck in the hopes of being able to do any job that's out there for us.
It's an M936. It did 30 years of service before it was retired, and then we found it.
The Green Giant saw minor action, retrieving a stolen camper. But today, Reliable's secret weapon will face its first real recovery.
Somebody sent us some photos about a pickup truck that went down an embankment off of Highway 5.
Following behind in a Reliable 4x4 one-ton
This military truck is very slow.
is operator James Luke.
It's pretty big, pretty badass looking, and it's definitely going to be fun to play with.
At our destination.
Dylan leaves the highway.
Gotta pack it into the bush.
And ventures where no roads go.
The 6x6 is pretty much going to be the one that we're using for terrain that's not everyday.
But in a field below the coast,
Holy fudgicles.
looking for a single wreck,
Someone in off right there. And there.
they discover double the challenge.
Wow. This is insane.
Near Merritt, is on the road to the extreme.
People that had left the road.
Double whammy.
We actually discovered that there's another vehicle the same make of truck.
So this is the first one, right? Second.
This was first, second.
He was
Also on scene is longtime team member Rooster Merkley.
Why is this here? Two separate accidents in the exact same spot.
Wow. What are the odds? Hopefully we get this done nice and quick.
For the last several winters,
Time to pop a rooster.
Rooster's been working hard for Reliable,
Okay, Roosty.
hoping to move up the ranks.
A cock-a-doodle-doo.
My goals are just to keep a roof over my head, eventually get into the bigger trucks.
He's that type of person that if we give him any kind of challenge, he'll meet it.
But today's recovery
How fast do you think he was going?
is double what they bargained for.
It'll make the day a little more challenging.
Seems to be a hot spot.
The pickups are in a patch of trees 100 feet uphill from the military truck.
Yeah, that's on a roll. Probably bring him to here and then nose over there and pull him down that way.
Working from the extreme spot,
Running off the road there.
problem.
Next time, on Highway Through Hell. Buckle up, side and back. Test firm and the rotator. Brakes, swings back into action. On a super-sized challenge. And a face from the past.
As long as it comes in one piece, I'm happy.
Makes a heavy rescue combat.
It arcs, explodes, and blisters steel. It's used to make 50% of all products. And it puts the power to build a skyscraper in a man's hands. By friction or robot, even underwater. These are the tools that the world can't live without. Now, welding on Modern Marvels. Las Vegas, Nevada. Perhaps nowhere else in the world does the old come down as spectacularly. And the new rise up as quickly.
Right now you're in the East Wing, the new Plaza Hotel. We're on the 38th floor. There we go, land deck.
The Palazzo Hotel will be the central hub of the world's largest resort, hotel, and casino complex. And without the power of welding, it couldn't be built. Armed with high-power welding guns, and with nothing more than a safety harness between them and the ground below, these ironworkers will weld a quantity of steel nearly equal to the amount in the Brooklyn Bridge, Statue of Liberty, and Empire State Building combined.
There's just shy of 70,000 tons of charging.
Adrenaline runs high for welders working at such heights. And with so much electricity in use, the dangers are real.
This particular machine runs on 483 phase. It's fed with 200 amp. At 480, you make a mistake, you're not here tomorrow. It's almost instantaneous death.
By definition, welding joins two separate pieces of material through high energy. No other joining method forms a more direct and powerful bond.
All the other methods, whether it's rivets, whether it's bolts, even if it's glues and adhesives, you wind up putting in extra material in order to make the connection. In the case of welding connections, bring the two pieces together, put a weld in between. It's a very efficient way of joining material.
But efficiency is only half the story. Because welding creates a bond along a seam or joint that is nearly always stronger than the base metals used to form it.
The tensile strength of the weld material itself is actually greater than the material you're welding. A good weld, the material itself will tear before the weld will tear.
The source of this strength is more than just surface deep, and goes right down to the steel's very atoms. Every atom within a beam possesses electrons that encircle it in what is called an electron cloud. When a welder applies intense heat, the atoms are slammed together so forcefully that they begin to share a single united electron cloud. Now locked as one, these new molecules are more powerful together than separate. For many centuries, the only way to make these welded bonds was with furnace and hammer, a process now known as forge welding.
With forge welding, two pieces of material are put lapped over each other, heated, not to the point of melting, but until they're hot, and then hammered together. That hammering together of the two metals will achieve the same metallic bonds that today we form with an electric arc.
Today, electricity has replaced the brute force of the forger's hammer to construct our world. From the car you drive, to the plane you fly, and everywhere in between. The most common method is known as electric arc welding, which is based on principles first discovered at the turn of the 19th century. Those principles revealed that electric current will jump the gap between two nearby metal conductors to form a completed electrical circuit. This jump, known as an electric arc, generates a spark-like discharge that is both extremely bright and intensely hot.
The arc is estimated to be between 6,000 and 8,000 degrees Fahrenheit. That's the same temperature as the sun. Steel melts in and around 3,000 degrees, so this 6,000 to 8,000 degree arc is more than ample heat to melt the steel that we're joining.
By the 1890s, engineers had harnessed this intense newfound energy to create the first electric arc welds. A work lead or ground was attached to one corner of the metal to be welded. Electric current then flowed from a generator through a long conductive metal stick known as an electrode. As the stick neared the grounded metal, an electric arc was formed, causing heat to melt the metal. The apparatus was crude, but the basics were sound, and are now reflected in the simplest arc welding form in use today, stick welding.
The basics of the process are, you have an electrode holder, you have a cable that runs back to the machine to pick up the welding current, and you place the bare end of the electrode in the holder, and it picks up electrical contact there, conducts current down to the end of the electrode, which is bare. The technique is touching the electrode against the work and then moving it far enough away to establish an arc, but not so far it goes out. And if you leave it too close,
Yeah.
it'll stick. You pull it away too
Yep,
far, it'll
I do.
go out. So the trick is to get your bounce.
We can also
where
have the
it's just about
GPS in the window, but I took it
When
out.
the arc is struck and positioned near the metal pieces, the intense heat causes both the electrode and the metal along the seam to melt together into what is called the puddle.
Okay.
Until it hardens, this molten puddle must be protected, even from the very air that we breathe.
The air we breathe is about 80% nitrogen and about 19% oxygen.
Yeah, you could.
Really good for
I could
breathing.
turn it to
It's not good for
whatever I
liquid metal.
want.
And
I would
just
just
like we dissolve sugar
pick
in
something.
hot coffee, these gases dissolve in liquid metal. When the metal solidifies, the gas
You can do. Oh, I may have made it wrong. You do YouTube. You could do movie sites, movies, Hulu, whatever you wanted.
So to shield the puddle, a chemical coating
You
is
could
applied to the
stream Discord to it if you,
As it melts
you know
over
what I
the heat
mean.
of the
If,
arc,
not that you
this
want to do
chemical
that, but
coating dissolves
it could
into
just
shielding
pick up any
gases
kind of
that envelop and protect the weld,
stream
keeping it
capture,
free of air.
pretty much. Let's
This is
see,
known
FA.
as shielded metal arc welding. And as the technology
You can just
evolved,
go through and
the
pick
coating took on even greater
whatever.
significance.
Like,
The chemical coating has
does
three
it switch
functions.
over to the Discord?
Some of the coating
I don't
forms
know if
shielding
that's
gases at
see
the
it.
heat of the arc to protect the
Yeah.
weld
Oh yeah,
from
it's
the
got to see
atmosphere.
it. Long as it's
Some of
up
the chemicals
somewhere,
at the heat
can't
of
be
the arc form liquid
minimized on the
slag,
screen.
protects the
Just
weld
has
as
to
the
be
shielding gases move
fully
along.
maximized. But
And some of the
like
elements
it
are alloyed
changed
into
to
the deposit to make it a high
the
strength deposit.
Discord and
So three things happen
back to
while
the
you're moving this arc along the work.
YouTube
When the weld is complete and is
browser,
cooled,
pretty much.
the slag is chipped away to reveal the trail of welded metal.
Pick
known as the
scroll. It's just my browser.
Getting the proper length,
Pick
thickness,
anything I can
and
do.
tone of the metal
Hopefully, I
along the
wouldn't
way
get strikes against
takes years of
me
practice.
because I'm watching it as well.
There's so many variables when you weld. It's very
Oh matter.
difficult
I'm
to
just
decide
messing.
two things you weld together are the same. Either the metal changes, the thickness of metal, the environment you're in, the conditions the metal is used for. There's just so many things change that you have to know a lot of different things about welding.
Complicating matters are the safety requirements, beginning with the welder's mask. Just as staring into the sun can damage your eyes, so too can an electric arc. Therefore, protection is crucial.
When you first flip it down, it's dark. You can't see anything, but you quickly get comfortable with it. Once you strike the arc, it's like a big flashlight. You can see what you're doing.
It ain't just the color. You can lighten it, darken it. When you play YouTube, you could do like it can pick YouTube and Spotify and all that. You can paste links in there. If you had a playlist or whatever, it'll load those up, and then you can set some controls to forward, next, and play and stop. It has all kinds of little binds you can do as well. Like on the long hauls, I'm putting up a movie and putting it over on my other monitor or whatever anyway, and I come across the plug-in and I'm like, hey, let's try this. And there you go. Oh.
Significantly, rivets limited the design options for architects and building engineers.
A lot of very famous and beautiful work is done with rivets. But basically you're building a box with a design to the inside of the box. You can only carry so much shear on that connection.
In 1928, Lincoln Electric joined with a local architectural firm to erect the first commercial building wholly constructed from arc-welded steel. In the Upper Carnegie Building, the typical dense network of riveted steel was replaced by a series of continuously welded beams that ran the entire length and height of the building. Not only did welding free up space, but these continuous beams carried even greater loads and stresses than their riveted counterparts.
Connections are always the weak point in a structure. Connecting things together is always a challenge. But welding changed all that. Literally, if you could get the material in the configuration you wanted it, there was a way to weld it together.
Today, skyscrapers come in many shapes and sizes, in large part because continuous beams can be fabricated and welded into curves and unique angles. To construct these beams, welders will make 30 to 40 passes in the crucial joints, using Lincoln Electric's latest flux core welding technology. Here, traditional stick electrode has been replaced by wire on a roll that feeds directly into the welder's gun. The chemical flux that protects the weld from the air is now contained within the wire itself and melts just as before.
There's approximately 90 tons of weld wire will be used and consumed in this project alone. That's somewhere around 180 billion inches or 2,800 miles of weld wire. You could stretch a single wire from LA to New York and have leftover.
On the largest beams, which can weigh as much as 900 pounds per linear foot, a team of welders can work on a single weld for hours.
The columns that we're looking at right now are basically supporting the entire east wing of this tower. Originally, these pieces were so long, the capacity of the cranes would not pick them up and set them. So we had to cut them down, make them lighter, so the crane could set them. And the engineers wouldn't allow us to make that a bolted splice. It had to become a welded splice. It's about a 30-hour weld. I believe we had 2 guys working on that simultaneously for 30 hours of welding.
Welding really enabled the architect, the engineer, to dream bigger dreams, make bigger bridges, make taller skyscrapers, and do so in a reliable and dependable way.
But at the end of the day, those big dreams are only as solid as the iron workers who weld them together.
We're not presidents. We don't get monuments built to us. But when you look across the skyline, iron workers have changed the way that looks.
But electric arcs aren't the only way to make a weld. In fact, others are a real blast. Pennsylvania's Allegheny Mountains, birthplace of American steel. Here in the hillsides that surround historic mill towns, the most powerful welding process of all occurs, more than half a mile underground.
Fire in the hole!
Move.
It's called explosion welding. And with a force measured in millions of pounds per square inch, explosion welding does what no other welding method can. Join nearly every kind of metal together, no matter the type or composition.
Explosion welding allows highly dissimilar metals such as aluminum, carbon steel, alloy steel, stainless steels, alloys of copper, all can be welded to one another.
The result? A single welded piece known as clad that combines the best characteristics of each metal involved. Wherever there is high heat, intense pressure, or corrosive liquids and gases, clad is probably there.
Could be a
Your
column,
man
could be a heat
get
exchanger,
clad, not
could be
glad.
a horizontal tank. But when you see a chemical complex or an oil refinery, there'll be a lot of clad metal in there.
To create an explosion weld, two large pieces of metal are stacked atop one another, then covered with a high-powered explosive. When detonated, the downward force of the explosion welds the two pieces together through a combination of intense force and remarkable physics.
What you can see here, and it's very clear, you have two different materials. Stainless steel is a darker gray, a lighter gray for the carbon steel material. The detonation was initiated at this point, and you can see the deformation from our initiator. That starts the explosion, and the explosion rolls across the entire top surface of the plate, zipping the two together.
No one would have ever thought such a violent process could be controlled and mastered had it not been for the devastation and havoc of World War I, and later, World War II.
The origin of explosion welding was first observed during the First World War when shrapnel may have stuck to armament. It wasn't just stuck, but it was actually welded.
There was only one possible explanation: the explosive force these metal pieces had endured.
It was an observed phenomenon that was later duplicated in the laboratories and in practice commercially.
Today, Dynamics Materials Corporation is a world leader in explosion welding technology. Here, the decades-old discoveries from the battlefield have been refined into an exacting science. The explosion welding process begins as soon as the two metal plates arrive at DMC's main plant, outside of Pittsburgh, Pennsylvania. To maximize the welding force of the explosion, the surfaces of each plate are ground as uniformly flat as possible. A process that also removes any rust, oxides, and other surface flaws. They're then ready to be assembled into the pack, which locks the plates into position for the explosion. To build a pack, the stronger and thicker of the two plates is laid face up. From now on, this plate will be identified as the backer. Small metal spacers of equal height are then tacked onto the surface of the backer in a uniform grid. These spacers will maintain a set gap between the backer and the second plate, which is placed on top. This second plate is thinner than the backer and is called the cladder. The standoff gap between the backer and cladder is less than an inch in height. Yet without it, the explosion weld would be impossible. In the final stage of assembling the pack, a folding wooden frame is constructed along the edges of the cladder. When this frame is later unfolded inside the underground explosion chamber, it serves as the bed for the explosive powder that is poured on top.
The three essential variables of an explosion weld are, first, the standoff gap, the spacing between the two metals needs to be very tightly controlled to ensure the highest quality weld. The second two parameters deal with the explosive. One is the velocity of the explosive, the speed at which it burns, and the height of the bed or
Driver,
quantity
you're getting
of
close to your
explosive
delivery.
which is evenly spread
Slow it
on
down
the
and get
top
ready
plate.
to enter the facility. Check in with receiving when you arrive and let us know once you're backed in and ready to unload. Dispatch out.
The amount and
this
exact
one,
formulation
there goes
is always
Tractor
matched
Supply.
to the types of metal involved.
Heads up.
Once the pack is set, everyone evacuates the chamber except the blaster in charge, who remains to wire the detonator.
The old blaster
He
in
will
charge.
be the last to leave the chamber.
Driver,
After
you're
all
getting
personnel
close to
are
your
accounted
delivery.
for, the
Slow it
blaster
down and
connects
get
his
ready to enter the
initiator switch
facility.
to the detonator
Check in
wires
with receiving
and
when you
fires the
arrive and let us
explosion.
know once you're backed in and ready to unload. Dispatch out.
The explosion is detonated from one edge of the cladder and moves across the upper level of the pack at a uniform speed. This explosive front progressively drives the cladder plate downward toward the backer at the slight collision angle caused by the standoff gap. Forward of the collision point, air is forced out of the gap at high velocity.
Yes.
All oxides and impurities are expelled, rendering the plate surfaces metallurgically pure and ideal for a weld. As the backer and cladder collide, the weld is created nearly instantaneously across the entire surface of the plate.
Look where I see it now. Tractor supply.
Because of the intense dust created by the explosion, workers can't retrieve the newly formed clad from the explosion chamber for more than 18 hours. Not surprisingly, the power of the explosion can cause significant deformation to the newly formed clad. Therefore, upon its return to DMC's central processing facility, the clad undergoes a final series of corrections. These include heating the clad in an oven that causes the metals to soften slightly. This relieves stress from the blunt force of the explosion's impact. Any bowing or misshapen curves are flattened out by either a 3 million pound press, or for thinner clad, by a series of rollers, known as levelers. Finally, before the material is shipped, stringent testing is conducted to ensure a solid weld between the two plates.
There's a lot of testing because generally these metals will go into a very high pressure vessel. The stakes are extremely high if
Driver,
there's a failure.
your arrival at the
So
delivery has
the
been
owners of
confirmed.
big
Go
plants
ahead and get unloaded.
chemical
Finish up any
manufacturing and
paperwork
oil
they need.
refineries are
And stand by
extremely
once you're
concerned
done.
that their materials
Dispatch out.
are what they ordered and specified. There's really no room for error.
Once the material has been proven to meet exacting specs, it's ready to be shipped to the customer. But explosion welding isn't the only adventurous business, and may look downright tame compared to welding 325 feet below the ocean surface. It's a rule that defines common sense. Don't mix water with electricity. It can kill you. But there is a rare breed of experts who dare to swim against convention and perform a job that most consider downright crazy. Underwater diver welders thrive on the dangers of the deep, where visibility can be zero and deadly hazards the norm. Why? To perform the perfect weld.
You're underwater and playing with electricity. It doesn't seem like a good combination, but it works quite well.
Over the last 30 years, the ocean depths have become vast job sites for the energy and communication industries.
This encompasses everything from pipelines to platforms to subsea wells to inspection, repair, and maintenance. We're working in water depths up to 10,000 feet.
Global Industries is a leader in offshore construction, engineering, and support for the oil and gas industries around the world. And to meet this constant demand, Global Industries requires their welding teams to undergo years of specialized training for all types of offshore environments.
We're here at our Research and Development Training Center here in New Iberia, Louisiana. We're dressing out our diver now, getting ready to get into the tank and do some training, do some welding.
There are two basic forms of underwater welding.
Cup of coffee.
Wet welding and dry welding. Wet welds are the most common and can be shielded metal arc or stick welds made by a fully submerged diver welder in a wetsuit.
Up
The
here.
electrode is waterproof and inserted into an electrically charged rubber encased stinger. Once struck, the electric arc burns just as if it were on dry land, since water is equally conductive. Likewise, the electrode's unique waterproof coating shields the weld from water contamination. But in case you're wondering, his rubber gloves are the only things that stand between the diver welder and electric shock.
If you have a hole in that glove, then you grab a hold of that live stinger, and that will give you a real good one, and you'll taste your fillings in your mouth.
Fortunately, the odds of a fatal shock are slim, because the welding equipment operates on DC current, which is far less dangerous than the ordinary AC current found in a typical home.
Calm check, calm check.
Right. Let's go see what's
To get the diver welder fully suited, 2 other diver welders act as his tenders, checking and testing every piece of equipment, including the helmet. Not only does the helmet provide air for the diver welder to breathe, it also serves as a full welding mask, protecting his eyes from the intense arc light.
Right here we have the lens plate, the face lens that a diver will flip down when he's ready to start welding. He'll flip it up when he's finished welding and take a look and see what he's doing.
Oh, heck no.
After the diver welder is suited up, he carefully enters the water and makes his way to the bottom of the tank. From the moment he puts on his helmet, the diver welder is in constant communication with the control room via audio links and a video feed.
Tom check 1, 2, 3. How do you got it, John?
Hey.
All right, set up the weld.
The trainee must not only learn to strike and maintain an arc, but he must also be able to connect and reset all of his equipment, including the electrode. Once in the water, the electrode is inserted into the stinger, which is termed cold, because the control room has not yet turned on the electricity. When the diver is ready to weld, he requests that the current be turned on.
Diver, making it hot.
Like every surface welder, the diver welder must be a master of concentration and stability.
You're going to have a lot of things that can interfere with what you're doing when you're welding. Just the surge of the ocean can push you around. Some divers like to actually put their hands up, hold the rod itself, because it gives you a lot of feel on it. If you just have the rod in your back, way back here from where you're working, you don't have the feel that you need.
Even fish can become distracting and potentially dangerous obstacles.
Barracuda like to watch. It's a giant fish. It looks like a torpedo with nasty teeth that stick out everywhere. And they like just to kind of hover over your shoulder to see what you're doing all the time. And you're just kind of like, what's that? But it's doing their own thing.
But sometimes a job requires a diver welder to go to extreme depths and stay in that environment for days, even weeks. This is called saturation diving and requires serious courage. It may also require the highly sophisticated technologies of dry underwater welding.
The difference between wet and dry underwater welding, the dry underwater weld will require a habitat. A habitat is lowered down and put in place on the member or on the pipeline that's going to be repaired. Once it's installed, they seal it, and then they actually put the air down to it and pump all the water out of it. This allows that piece to be basically dry now. And so the divers can go down, and they'll actually climb up inside the habitat, remove their helmets, and actually be able to go to work and weld that particular item in the dry.
Dry underwater diver welders work in pairs and in 6 to 8 hour shifts. When done, they return to the surface in a diving bell, then enter a second habitat maintained aboard ship. Within these on-ship habitats, they will eat, sleep, and relax before returning to the ocean floor. Both the diving bell and on-ship habitat maintain the same pressure, as if the divers were still 1,000 feet underwater. This is the only efficient and practical way for their bodies to remain adjusted to such extreme pressures. Otherwise, the diver welders may experience the bends and other physical perils, even death. To prepare diver welders for these conditions, Global Industries has built an unparalleled underwater simulator.
This facility that you see behind me right here, it's really the only one of its kind in the United States. We call this the dry pot. We can carry out dry welding scenarios down to 1,000 feet.
A hyperbaric chamber simulates the high pressures the human body must endure when working at great ocean depths. Akin to being an astronaut, a trainee will spend more than a week living in this simulated environment. And conditions are tight.
It's very, very cramped inside there. So there's a place for everything to go, and you have to be sure that you put everything in its place before you go and start doing things, because there are a lot of things that can bite you in there.
Ain't no spiders.
Unlike the wet welder, the dry welder can perform more than stick welds in his cramped habitat.
I'm standing right in front of the entrance to the dry pot hatch. Royce is doing gas tungsten arc welding. It's also known as TIG welding.
Go down the road, man.
Tungsten inner gas.
Drifting off the road. Just
Once his training is
stay
finished,
straight.
the trainee enters this decompression chamber to slowly acclimate his body back to the normal atmosphere. But while even these adrenaline junkies need to rest once in a while, some welders never take a break.
You got a red
Of
Jeep.
course,
Good job.
They're robots. Welding, the heart and soul of making a car. And for major automobile manufacturers like General Motors, no process is more vital or more automated.
When I first started with General Motors, there weren't any robots in the body shop I worked in. 2 years later, there were 40 of them. In the body shop we're standing in now, there's approximately 1,200 robots.
Holy.
Over a third of them,
1,200 robots.
some are welding robots.
Here at GM's Lake Orion assembly plant, more than 16,000 cars roll off the
And
line
cars
every
still
month.
cost a lot of money?
By the time each
I
car
thought
is
the
fully
robots
assembled,
work for free.
it will contain thousands of welds.
Sounds like a robot's got a retirement plan and everything with the price of cars. Damn.
Once the outer structure goes on, there'll be approximately 1,200 more welds added to it for approximately 5,000 welds overall on the vehicle.
Nearly all those welds are completed by robotic welding systems, which load, position, and weld more than 240 component parts.
Most of the robots that are used for welding are actually used for spot welding. And probably 60% of the welding robots that are out there are actually spot welding robots.
Unlike arc welding, spot welding does not create a bead, nor is it designed for heavy steel items like beams. Instead, spot welds bond thin metal sheets, as in car doors or hoods. Energy is focused to a single spot, where two electrodes make direct contact with the metal sheets to be joined. The electrodes are made of copper because it has low electrical resistance and high thermal conductivity. This means it can deliver some serious juice.
This particular unit is a pneumatic operated spot welding system. It's got a 75 kVA transformer back here. The electrodes up here are all water cooled. This particular setup here probably runs about 10 to 12,000 amps through these electrodes right here. It's not uncommon to see 40, 50,000 amps run through the electrodes.
Given that most houses run on less than 200 amps, that's a lot of power. But it's not the only factor in a reliable spot weld. You need pressure. When the two electrodes come together, they pinch the two metal sheets at the spot and cause a small indentation in both. Electric current then begins to pass from one electrode to the other through this spot in the sheet metal. As it does so, the current that flowed so smoothly through the copper now encounters resistance in the less conductive metal pieces. This resistance results in heat, and the metal begins to melt, causing a molten nugget to form. When the molten nugget cools and coalesces, It locks the two metal sheets together. The electrodes then release the pinch point and move on. A robot can make a series of spot welds in a relatively short period of time. For a man, it's a heavier task.
A typical spot welding gun might weigh anywhere from 100 pounds to 200 pounds. That's a lot of physical labor to move a spot welding gun. And so a robot that's designed to handle that kind of weight is an ideal setup because the robot can just handle the spot welding gun and consistently put it in the same place every time.
Factor in the sheer number of spot welds required to assemble a car, and robots make an incredibly practical solution for car manufacturers. And advances in recent technology allow robots to reach further, work closer together, and execute a greater variety of welds than ever before.
The robot can pretty much weld the same speed as a man.
Yes,
Where the payoff is,
oh, I got a long ways to go.
it's
Got an hour drive.
always welding. A man has to weld and then lift his hood up and adjust the part and put the hood back down and re-weld again. Where the robot's just going to weld. It might have a 85% arc time compared to a manual of 20%.
It took a man about 3 hours to make this particular product. Now that the robot's welding it, it takes essentially about a half an hour to weld the entire part.
But today, robots aren't just spot welders. Here at RobotWorks, a leader in robot system integration, robots execute nearly every form of welding, and often in surprising ways.
This system has the capability of running at about 30 to 40 inches per minute of weld. This system is unique in that there's two technologies that are actually integrated into it. One called touch sensing, another called seam tracking. What touch sensing allows the robot to do is actually find the seam. It would come down, sense that it has touched the part in one specific spot, record that data, save that positional data. It would then come up, sense the next spot doing the same process. And at that point in time, the robot would know from the trigonometry where that seam starts. There's another technology called seam tracking. What that allows you to do is once the robot has found the seam, it actually allows the robot to stay within the seam throughout the course of the welding.
But even as robots become more sophisticated and commonplace, they will still require HMI, human-machine interface. After all, someone still needs to program them, and he or she better know welding.
So the program really suggests to take a guy that's a welder because he's going to know, like if he hears an arc and it's not right, he'll know that it might be because of the shielding gas or the stick out the robot's using because he knows welding. But a guy that doesn't know welding might think it's because of the robot controller or something to do with the robot. Somebody that understands the process is the best kind of a robot operator programmer.
Think robots are innovative? Well, you haven't seen, or should we say, you haven't heard anything yet.
Moral of that story, be smarter than the robot.
Say welding, and you immediately think iron, steel, metal on metal. But today you can weld just about anything, including plastic. Plastic toys, plastic packaging, and lots of household items are welded together by a process known as friction welding. Friction welding comes in many forms, yet all work essentially the same. They generate heat through mechanical action, like the high-speed rubbing of two sticks together. With plastics, the best friction welds are made through the power of sound. It's called ultrasonics. Ultrasonics utilizes the high-intensity acoustic energy that occurs in frequencies beyond human hearing. The sound waves cause the plastic pieces to literally vibrate against one another at high intensities. At that interface, heat is generated, and the two pieces fuse together. It happens so fast that the naked eye can't see it.
People don't realize the amount of power that is available in sound waves if the sound waves are focused properly. And these materials are vibrating, in many cases 20,000 times per second, 40,000 times per second. That frictional heat is so intense that the plastic welds within a fraction of a second.
In 1964, Robert Soloff received the first ever patent for ultrasonic plastic welding. Today, his company, Sonics and Materials, builds the technology that welds everything from toothpaste tubes to coffee makers to simple toys. At their headquarters in Newtown, Connecticut, ultrasonic welding machines are manufactured to precise specifications, or else the welds wouldn't be perfect. There are 4 main parts in an ultrasonic welder: a power supply, and 3 components known as the ultrasonic stack.
This is the ultrasonic stack for the ultrasonic welding press, which is comprised of the ultrasonic converter, the booster, and the ultrasonic horn.
The power supply takes standard 60 hertz power and pumps it up to 20,000 hertz of acoustic energy. This acoustic energy causes coin-sized ceramic discs within the converter to physically expand and contract, creating 20,000 mechanical vibrations per second. These vibrations are then focused to the plastic parts, first through the booster, then through the horn, which delivers the vibrations directly onto the plastic parts to be welded. Although sparks don't fly during ultrasonic welding, it still gets the job done.
No sparks don't
This happens
fly.
to be a 2-piece whistle. So we take the 2 pieces of plastic, we put them in a lower fixture. The fixture is made to the application, to the piece of plastic, and then we have a very basic flat-faced ultrasonic horn because the part is flat. There's no contours to the part. So that quickly, we just welded the 2 pieces of plastic together in 0.24 seconds. What I'm going to do is take a screwdriver and break the plastic apart at the weld area. And in turn, this will show the molten white plastic where it's bonded to the red plastic.
And thank Ultrasonics for the hermetic seal on clear plastic packaging.
Thanks.
You know, the plastic you can never quite get open.
That's the person who did it.
We have these
Send
PVC
your fan mail
clamshells
to
or
them.
tamper-proof clamshells so that the product can't be easily removed from it or put in a pocket. Ultrasonics is commonly used to seal these clamshells. And now we have ultrasonically welded the edge of the clamshell.
While ultrasonics occurs in the wink of an eye, another form of friction welding will keep your head spinning.
Spin welding is rotary friction under pressure, which generates heat in the joint area to melt the plastic and fuse the parts together.
A typical insulated coffee mug is spin welded from 2 parts. A suction device grabs hold of the inner shell and rotates as it descends into the outer shell. The collision of the stationary and rotating pieces generates heat, causing the plastics to soften. When a braking system stops the rotation, the softened plastic seams of the 2 shells fuse as they cool. The result? A perfect hermetic seal. So from ordinary household items to structures of extraordinary heights and depths, welding plays a crucial role in everyday life by simply joining the world together. It arcs, explodes, and blisters steel. It's used to make 50% of all products, and it puts the power to build a skyscraper in a man's hands. By friction or robot, even underwater. These are the tools that the world can't live without. Now,
There are homes in the world that make you wonder whether they were built to adapt to nature or to challenge it. From villages clinging to cliffs and towns squeezed into narrow mountain gaps to living spaces created under extreme natural conditions. In some places, people live under relentless rainfall, where mud and dense fog become part of daily life, while in others, they survive in dry, harsh environments where every condition pushes human limits. These spaces are not just shelters, but evidence of human resilience and the ability to endure in the face of extreme surroundings. This is a journey into the most surreal houses on Earth, where the line between architecture and environment almost disappears. Hue Ki, Vietnam. Surrounded by Green Mountain Forest, this village looks as if it was built entirely from stone, because everything from the houses to the paths shares the same cold gray color. The first homes here were built from about 1594 to 1677, linked to the time when the Mac rulers retreated into the mountains and turned this place into a defensive base. For the Tay people, stone is not only a building material, but also a guardian spirit. So each house carries the belief of protection from danger. The walls are about 2 to 3 feet thick, and many parts were stacked fully by hand without cement, yet they have stood strong for centuries. Each house has 2 levels, with the lower floor for animals and tools, and the upper floor for living, which keeps the inside cool in summer and warm in winter. When moss covers the stone walls and the village paths shine after rain, the whole place feels quiet, ancient, and deeply mysterious. Wooden churches of Arkhangelsk, Russia. In the frozen taiga forest near 64 degrees north, these wooden churches appear like fairy tale castles, standing for 300 to 400 years without a single iron nail. Ancient craftsmen joined pine logs more than 100 years old with flexible wooden joints, helping the buildings expand with the seasons and survive cold down to minus 40 degrees Fahrenheit. The sharp tent roofs rising into the sky are not only spiritual symbols, but also help snow slide down quickly so its weight cannot crush the roof.
Great Depression still hung in the air. Most people were pulling back, playing it safe. Theodore Alfred Peterman wasn't one of them. In the forests of the Pacific Northwest, he was bleeding money. His timber stacked and rotting while trains ran late or not at all. The railroads held all the power. Peterman was done waiting. So he got his hands on a batch of retired trucks, tore them down, rebuilt them from the axles up. This wasn't ambition, it was frustration turned into
crazy waste station.
What started in a garage became something far bigger. Peterbilt. And it all began with a logging problem. Let's rewind to America in 1939. Banks were failing, factories were shutting down. The Great Depression had crushed dreams across the country. Yet somehow, in this economic wasteland, a lumber baron named T.A. Peterman was about to start a truck company. Most people would call that crazy, but Peterman wasn't most people. Born on March 22, 1893 in Tacoma, Washington, Theodore Albert Peterman had spent decades wrestling with one problem that drove him absolutely mad. Moving logs from forest to mill meant dealing with railroads that charged whatever they wanted and ran on schedules that ignored his needs. Weather delays meant logs rotted while waiting for transport. Peterman watched perfectly good timber turn into expensive firewood because he couldn't control how it moved. The lumber industry had always accepted these limitations. Peterman refused to. His first attempt at a solution came in 1934 when he bought 15 old white trucks that had been retired from service by the Shell Oil Company. These weren't pretty machines. They had hand cranks instead of electric starters, solid rubber tires that punished every bump, mechanical brakes that barely worked. But Peterman saw potential where others saw forgotten equipment. He ripped out the hand cranks and installed electric starters. He swapped those bone-jarring solid tires for pneumatics. He upgraded the braking systems to air-powered units that actually stopped the trucks. Most importantly, he developed trailer rollers that prevented dangerous momentum transfer during transport. Each modification was an innovation, sparked by real-world frustration. By 1938, Peterman's modified trucks had proven themselves in the brutal world of Pacific Northwest logging. But he wanted more. He wanted trucks built right from the start, not cobbled together from retired surplus. That's when he heard about Fager Truck Company in Oakland, California. The company was bankrupt, and its owners were desperate to sell. Most business experts would have run from a failing truck manufacturer during the Depression. Peterman saw opportunity where others saw disaster. The risk was enormous. $50,000 equaled nearly $950,000 in today's money. Peterman was betting everything on a company that had already failed once. The Fajol plant sat on 13.5 acres in Oakland. It came with tooling, parts inventory, and engineering expertise that nobody else wanted. But Peterman understood something his competitors missed. He wasn't just buying a factory, he was buying the ability to build trucks exactly the way truckers needed them built. In April 1939, Peterbilt Motors Company released its first vehicles. The Model 260 featured single-axle design with chain-drive transmission and a curb weight of 32,000 to 37,000 pounds. This wasn't an accident. Chain drive delivered maximum pulling power at low speeds, perfect for dragging massive logs up steep mountain grades. The Model 334 took a different approach with dual drive axles, shaft drive transmission, and the distinctive egg-crate grille that would become a Peterbilt signature. With a high-capacity payload design, this setup worked better for highway operations where speed mattered more than raw torque. Both Both trucks came with gasoline or diesel engines, giving customers real choices based on their specific needs. The engineering philosophy behind these first Peterbilts reflected Peterman's logging background. In the woods, equipment failure meant lost money, lost time, and sometimes lost lives. Peterman's engineers designed trucks based on first-hand input from truckers, learning what broke, what worked, and what needed improvement. This wasn't typical for 1930s manufacturing. Most companies built what they thought customers wanted. Peterbilt built what customers actually needed. The first Peterbilt ever produced wasn't even a truck. It was a fire truck chassis built for Hearst Fire Truck Company. They also added a hood, grille, fenders, and fire apparatus to meet their requirements. It was sold to the Centerville, now Fremont, California Fire Department in 1939. By the end of 1939, the company had built just 16 vehicles total. Production numbers didn't tell the whole story, though. Each truck represented hours of careful assembly and quality control that set Peterbilt apart from mass production manufacturers. While other companies rushed trucks off assembly lines, Peterbilt treated each vehicle like a custom project. The early trucks looked nearly identical to the old Fajol designs. Peterman had inherited the tooling and needed to maintain production continuity. But beneath the familiar appearance, something different was happening. The attention to detail that Peterman demanded resulted in trucks that simply worked better. Drivers noticed the difference immediately. These trucks handled better, lasted longer, and required fewer repairs than anything else on the road. Quality, customer needs, brutal durability. Peterbilt's creed came from Peterman's war with failing logging trucks. But as 1940 dawned, global events were about to test these carefully crafted principles in ways no one could have imagined. Those first Peterbilt trucks rolling off the assembly line in 1939 faced a test nobody predicted. America was about to enter World War II. Civilian truck production would screech to a halt. Material shortages would make manufacturing nearly impossible. For most companies, this would spell disaster. For Peterbilt, it became the crucible that forged their legendary reputation. The transition happened almost overnight. In 1941, Peterbilt introduced the Model 364, originally designed for the brutal demands of Pacific Northwest logging operations. This incredible truck featured reinforced chassis construction and heavy-duty axles that could handle loads other trucks couldn't even attempt. The 364 weighed up to 44,000 pounds fully loaded, making it one of the heaviest trucks available at the time. But before loggers could fully appreciate its capabilities, the military came calling. December 7th, 1941 changed everything. Pearl Harbor thrust America into global war, and suddenly every manufacturing facility became part of the war effort. Peterbilt's small Oakland plant found itself retooling for military production. The company briefly continued producing the 260-360 series trucks in 1942, before halting civilian production completely to support the military campaign. The company didn't close its doors, it reinvented itself. The Model 364 proved perfect for military applications. Its robust construction and reliable performance made it ideal for hauling heavy equipment, supplies, and personnel under combat conditions. The military placed substantial orders, with Peterbilt securing a major contract for 224 trucks by 1944. 28 Model 364s went specifically to the US Navy in 1942, where they served with distinction. War production forced Peterbilt to innovate in ways peacetime never would have demanded. Material rationing meant engineers had to find alternatives to traditional steel construction. The company expanded its wartime aluminium experimentation, building on experience gained from aluminium grills used since the Fajol days. This expanded use of lightweight materials during the war years would lead directly to Peterbilt's pioneering aluminium cab construction for civilian trucks in 1945. Using aluminium wasn't just a matter of necessity. It uncovered real advantages in cutting weight and resisting corrosion. The most significant wartime innovation came in 1942 with Peterbilt's first cab-over-engine design. This half-cab configuration with full-deck chassis emerged from practical necessity. Military operations required trucks that could maximize cargo space while meeting length restrictions. The cab-over design moved the driver's compartment directly over the engine, freeing up additional deck space for equipment or supplies. What started as a wartime expedient would become a cornerstone of modern truck design. Production numbers tell the story of successful adaptation. The company built 82 trucks in 1940, then ramped up significantly during the war years. By 1945, production had reached 324 units, nearly 4 times the 1940 output. This wasn't just quantity. Each truck maintained the quality standards that Al Peterman had established from day one. The Oakland plant stayed busy even during production, by renovating military surplus trucks from various manufacturers. This work provided Peterbilt engineers with unprecedented exposure to different design approaches and manufacturing techniques. They learned what worked, what failed, and how other companies solved similar problems. This knowledge would prove invaluable when civilian production resumed. But 1944 brought devastating news. Theodore Alfred Peterman died of cancer on November 16, 1944 in Vancouver, Washington at age 51, just as his company was reaching new heights. His wife Ida inherited the business but faced an impossible choice. She understood lumber. She didn't understand truck manufacturing. The decision to sell came quickly, but Peterman's engineering philosophy had already taken root too deeply to be uprooted. The end of the war in 1945 marked another transformation. Civilian production resumed with pent-up demand from industries that had been starved of new equipment for 4 years. Peterbilt's reputation for military reliability translated directly into civilian market credibility. Truckers who had operated military Peterbilts during the war knew these trucks could handle anything peacetime operations could throw at them. 1939's garage shop became 1945's industrial artisan. War taught Peterbilt to scale without sacrificing steel. But with Peterman gone and his widow uncertain about the truck business, the company's future remained far from secure. If you're enjoying stories like this, consider liking the video and subscribing to the channel. It helps more people discover these forgotten chapters of industrial history. The post-war trucking boom should have been the perfect moment for Peterbilt to thrive. America was building highways at record pace. The economy was exploding. Truck demand was skyrocketing. But inside Peterbilt's Oakland headquarters, the company faced a crisis that threatened everything Theodore Peterman had built. Ida Peterman found herself running a truck company she never wanted to own. After her husband's death in 1944, she inherited a business she didn't understand in an industry she'd never worked in. The logical solution came in 1947, when she sold Peterbilt's operating assets to a group of company managers and investors for $450,000. But Ida made one crucial decision that would haunt the company for the next decade. She kept the Oakland factory property for herself. On the surface, it looks like a simple transaction. Beneath it, a time bomb was waiting to go off. The new owners got the Peterbilt name, the manufacturing equipment, and the customer relationships, but they were essentially renting their own factory from the founder's widow. This arrangement created an uncomfortable dependency that left Peterbilt vulnerable to forces completely outside their control. The management team threw themselves into expanding the business. They introduced the Model 280 and Model 350 in 1949, offering both conventional and cab-over engine configurations. The iron nose conventional models featured aggressive front-end styling that projected power and reliability. The bubble nose cab-over designs maximized cargo space while meeting increasingly strict length regulations. More than new models, these trucks announced Peterbilt's intent to be a serious player in the post-war race for dominance. Production numbers climbed steadily through the early 1950s. The company was building trucks faster than ever before while maintaining the quality standards that set Peterbilt apart. In 1953, they even redesigned their logo, switching from the rectangular border to the distinctive red oval that still identifies Peterbilt trucks today. Far from being merely cosmetic, it showcased a stronger sense of who they were and where they stood in the market. But success couldn't solve the fundamental problem. Ida Peterman owned the ground beneath their feet. She controlled their destiny in ways that had nothing to do with truck manufacturing. The management team built their business on renting land, always knowing that their landlord might have different plans for the property. That nightmare became reality in 1958. Ida Peterman announced she was redeveloping the Oakland factory site as a shopping center. The decision had nothing to do with Peterbilt's performance or prospects, it was pure real estate economics. The 13.5-acre Oakland site had become too valuable for industrial use. Retail development promised much higher returns than factory rent. Pacific Car and Foundry Company had been watching Peterbilt's success with growing interest. The company already owned Kenworth Truck Company, giving them deep knowledge of the heavy-duty truck market. They understood exactly what Peterbilt represented. More than another player in the industry, this was Kenworth's fiercest rival, built on engineering excellence and a brand reputation that set it apart. The acquisition talks moved quickly once Ida Peterman's redevelopment plans became public. Pacific Car and Foundry saw an opportunity to eliminate their biggest rival while expanding their manufacturing capacity and market reach. For Peterbilt's management team, the company offered something they desperately needed: financial stability and operational security. On June 24, 1958, Pacific Car and Foundry acquired Peterbilt Motors Company. The deal solved multiple problems simultaneously. PACCAR gained a respected brand with proven engineering capabilities and established dealer relationships. Peterbilt escaped the uncertainty of factory relocation while gaining access to substantial financial resources and manufacturing expertise. The integration strategy proved brilliant. Instead of merging Peterbilt into Kenworth, Pacific Car and Foundry maintained both brands as separate entities competing in overlapping markets. It reflected not excess, but a deliberate branding strategy that catered to distinct tastes within the premium segment. Pacific Car and Foundry's commitment became obvious immediately. In August 1960, they moved Peterbilt to a new 176,000 square foot manufacturing facility in Newark, California. This wasn't just a factory relocation, it was a massive investment in Peterbilt's future. The new plant featured modern assembly lines, improved quality control systems, and production capacity that dwarfed the old Oakland facility. The results spoke for themselves. During the first year at Newark, Peterbilt delivered more than 800 trucks. Sales increased so rapidly that the new plant was already approaching capacity limits. By 1969, the company opened a second Peterbilt manufacturing facility in Madison, Tennessee, to serve East Coast markets and expand overall production capability. From precarious regional builder to industrial heavyweight, with PACCAR's backing, Peterbilt now had the tools to own the coming transportation revolution. The Newark plant's modern production capabilities unleashed 2 decades of engineering innovation that would redefine American trucking. Between 1960 and 1979, Peterbilt transformed from a regional truck builder into America's premium heavy-duty truck manufacturer. Not an evolution, but a revolution, ignited by engineering advances that pushed the boundaries of trucking. Under PACCAR's ownership, Peterbilt had the resources to think bigger, build better, and compete nationally against established giants like Mack and International Harvester. Triumph sparked fiercer battles as competitors attacked on every front. Long-haul operators wanted different features than construction companies. Regional haulers had different priorities than cross-country drivers. Meanwhile, Peterbilt found itself competing directly against Kenworth, its PACCAR sister company. This internal rivalry could have been destructive. Instead, it became the driving force behind rapid innovation as both brands pushed each other toward excellence. The pressure to differentiate sparked a revolution in truck design. The Model 282-352 cab debuted in 1960 with aluminium construction and larger windows, improving visibility and weight savings. This Unilite aluminium cab completely abandoned traditional all-steel construction. Beyond reducing weight, the Unilite featured larger windows that dramatically improved driver visibility. The instrument panel was completely redesigned for better ergonomics. The result was a cab that looked modern and performed better than anything competitors offered. Engineering advances came rapidly after the Unilite's success. The 1965 Model 358 introduced Peterbilt's first 90-degree tilting hood on conventional trucks and debuted the iconic bird hood ornament. Mechanics could finally access engines without crawling under trucks or removing heavy hood panels. Maintenance time dropped, repair costs fell, fleet operators noticed immediately. The bird hood ornament communicated premium quality at first glance. The Model 359 launched in 1967 represented Peterbilt's boldest design statement yet. This was the company's first long hood conventional design, featuring a massive grille designed to accommodate the larger diesel engines becoming industry standard. The design philosophy was described as big, long, low, and powerful. The 359 looked exactly like what serious truckers wanted to drive. More importantly, it performed like what serious truckers needed to own. Geographic expansion kept pace with product development. The 1967 opening of the Madison, Tennessee plant served East Coast markets while reducing shipping costs and delivery times. By 1973, the Madison facility had doubled its production capacity. Combined plants reached 8,000 vehicles annually. Peterbilt recognized that highway hauling was just one market segment. The company expanded into specialized applications.
Please.
And the refuse-focused CB300 for urban collection routes. By 1978, Peterbilt ended its joint venture in the CB300 and introduced the proprietary Model 310, establishing independent presence in the vocational market. Driver comfort became a crucial competitive advantage as the industry faced driver shortages. Peterbilt's 1972 introduction of the 1100 series cab featured 1,100 square inches of windshield glass, significantly improving forward visibility. Sleeper cab design evolved from basic 30-inch and 36-inch compartments to custom units by Mercury Sleepers. By the late 1970s, Peterbilt brought sleeper design in-house, developing a 63-inch sleeper with walk-through doors and raised roofs. The 1970 Model 348 introduced another industry first, an angled fiberglass hood on heavy-duty vocational trucks. This innovation reduced weight while maintaining durability. The angled design improved serviceability compared to traditional flat hood configurations. These innovations established the brand identity that defines Peterbilt today. Premium positioning based on superior engineering, driver-focused design that prioritized comfort and functionality, quality construction that justified higher prices through lower operating costs. The landmark production of the 100,000th truck in 1977 demonstrated how far the company had traveled from its origins as a small and custom builder. But as the 1970s ended, Peterbilt was about to discover that building great trucks was only part of the equation. The brand was poised to become something much bigger than a manufacturer. The cultural transformation began in the mid-1970s when CB radio licenses exploded from 800,000 in 1967 to over 11 million by 1977.
11
drivers
million.
transformed from blue-collar workers into folk heroes. CB radios turned highway conversations into nationwide entertainment. Songs about 18-wheelers climbed the charts. Movies made truckers the good guys fighting corrupt sheriffs and corporate villains. At the center of this cultural revolution sat Peterbilt trucks, not just as transportation equipment, but as symbols of everything Americans wanted to believe about freedom, rebellion, and the open road. The timing couldn't have been more perfect for this transformation. The 1973 oil crisis had triggered nationwide fuel shortages. The 55-mile-per-hour speed limit felt like government overreach to drivers accustomed to wide-open highways. Hauling freight was only part of the job now. Truckers had become savvy communicators, resilient travelers, and emblems of autonomy in a regulated era. While other truck manufacturers scrambled to capitalize on this cultural moment with aggressive, masculine marketing campaigns, Peterbilt chose a completely different approach. Here's what made Peterbilt's strategy brilliant. Instead of embracing the rough and tumble trucker stereotype, they elevated it. Their advertising campaigns during the 1970s emphasized class and elegance, specifically targeting women with fashion magazine-style photography, featuring sophisticated settings alongside gleaming Peterbilt trucks. These weren't ads selling work trucks. These were ads selling dreams. The message was clear. Peterbilt wasn't just better built, it was better, period. This positioned the brand as aspirational rather than purely functional. Peterbilt navigated the contradiction between romantic imagery and economic hardship by making their trucks symbol of professional achievement rather than just work tools. Owning a Peterbilt meant you made it in the trucking world. This wasn't about survival, it was about professionalism and having access to the best gear on the road. The Model 359, with its long hood and commanding road presence, became the visual representation of trucking success. When other drivers saw a 359 coming down the highway, they knew they were looking at someone who'd earned their place behind that distinctive grille. The CB radio culture sealed Peterbilt's iconic status through language itself. Pete became the official CB handle for Peterbilt road tractors in trucker slang across as a title that grew from real respect. Successful marketing alone couldn't explain it. This was cultural integration at its deepest. During the 70s and 80s, Peterbilt's influence went beyond sales. Their trucks became the standard by which all others were measured, how truckers should be portrayed, and what the relationship between driver and machine could represent. The brand had transcended its industrial origins to become part of American mythology. But as the 1980s ended and CB culture faded, Peterbilt faced a new challenge that would test whether engineering excellence could survive without cultural momentum. The 1990s hit Peterbilt like a wake-up call. No half measures here. The industry wasn't being refined, it was being remade. Fuel efficiency suddenly mattered more than raw power. Environmental regulations were getting stricter every year. Customers wanted trucks that could handle like sports cars while hauling 80,000 pounds. The old ways of building trucks wouldn't cut it anymore. Peterbilt had to reinvent itself, get left behind. PACCAR's global expansion created the foundation for everything that followed. The 1996 acquisition of DAF Trucks brought European engineering expertise directly into Peterbilt's development process. The acquisition went far beyond corporate expansion. It was a gateway to revolutionary technologies that had eluded American manufacturers. While US truck makers focused on power and size, their European counterparts had spent decades mastering efficiency and stringent fuel regulations. They'd figured out aerodynamics, lightweight construction, and advanced engine management systems that American truckers were just starting to demand. The first fruits of this partnership appeared in 1998, when Peterbilt launched the medium-duty 210-220 LCF trucks using DAF LF cabs, demonstrating how European technology could be adapted for American markets. But here's the thing. Having access to technology and actually using it are completely different challenges. The trucking market was fracturing into specialized segments that each demanded different solutions. Highway haulers cared about fuel economy and comfort. Construction companies needed maximum durability and serviceability. Urban delivery operations wanted maneuverability and visibility. Medium-duty operators required completely different capabilities than heavy haul specialists. Emissions regulations were tightening every few years. EPA was demanding cleaner engines. California was pushing even stricter standards. Meanwhile, fuel prices kept climbing. Diesel that cost $1.20 per gallon in 1990 hit $2.30 by 2005. Every penny per mile mattered to operators running razor-thin profit margins. The old Peterbilt approach of building premium trucks for demanding customers wasn't enough anymore. Premium had to mean efficient. Durable had to include environmentally responsible. Powerful had to work with clean-burning engines that met federal regulations. Peterbilt's engineers were essentially redesigning trucks from scratch while maintaining the brand identity that customers expected. The Model 387 launched in 1999 as Peterbilt's answer to the aerodynamics challenge. This wasn't surface-level styling. It was an aerodynamic revolution that redefined the truck's very DNA. The HUD featured dramatically redesigned contours that channeled air smoothly over the cab. The fenders were sculpted to reduce turbulence. Even the grille was engineered for optimal airflow rather than just visual impact. This represented Peterbilt's first wide-body cab design, shared with the Kenworth T2000, creating more interior space while improving aerodynamic performance. The result was significant fuel economy improvements compared to conventional configurations. Drivers could cover the same routes while burning less diesel. Medium-duty expansion opened completely new markets. The Model 330 debuted in 2000 as Peterbilt's first conventional cab truck, designed specifically for medium-duty applications. These weren't scaled-down heavy trucks. They were purpose-built vehicles featuring all aluminium cabs, tight turning radiuses, and steep hoods.
Anybody out there?
The Model 335 followed with additional configurations for specialized applications.
Did you
This
hear?
expansion demonstrated that Peterbilt could compete beyond traditional Class 8 markets while maintaining engineering excellence. The hybrid revolution started earlier than most people realize. Peterbilt introduced the Model 330 and Model 335 hybrids in 2006, years before hybrid commercial vehicles became mainstream. These diesel-electric systems combined the new 6.7-liter Packard PX6 diesel engine with parallel hybrid technology developed through partnership with Eaton Corporation. The hybrid models were expected to reduce fuel consumption by 30 to 40%, through improved on-road fuel economy and more efficient stationary operation. Not trials, not tests, just real trucks, saving real money on real routes. Vocational markets demanded their own solutions. The Model 365 and Model 367 launched in 2007 as purpose-built platforms for construction, utility, and specialized applications. These weren't highway trucks adapted for off-road work. They were engineered from the beginning for demanding vocational environments. Reinforced chassis, heavy-duty axles.
I like the video player on the dashboard.
Deep understanding of construction and utility requirements. The Model 389 arrived in 2006 as the ultimate expression of modern Peterbilt engineering, replacing the Model 379 after 2 decades of production. This flagship model incorporated decades of technological advancement while maintaining the essential design elements that made Peterbilt trucks instantly recognizable. The 131-inch BBC configuration featured redesigned headlamps, fenders, and trim alongside cutting-edge electronics, introducing smart nav systems and touchscreen displays. The 389 proved that advanced technology could enhance rather than compromise traditional Peterbilt styling. These innovations positioned Peterbilt perfectly for the challenges ahead. The company had proven it could adapt European technology to American markets. It had successfully expanded.
Yeah, it's like I found that video, freaking 100 gigabyte recording of a game. I had no idea.
Efficiency could coexist with the performance and durability that Peterbilt customers demanded. But the next decade would demand even more radical changes than anyone could have imagined. The 2010s forced Peterbilt to confront a technological revolution. Electric motors and autonomous systems advanced rapidly while tightening emissions regulations. Like California's diesel bans and corporate sustainability demands pushed the industry towards zero-emission solutions. Battery tech finally reached viability, enabling electric trucks to handle real workloads. Peterbilt's transformation began with the U.S. Department of Energy's Supertruck program, 2009, which reimagined truck efficiency through advanced aerodynamics, powertrains, and safety systems. Supertruck 2's 132% freight efficiency gain laid the groundwork for future electric and autonomous development. Where rivals saw a simple powertrain update, Peterbilt faced an existential overhaul, rewriting 80 years of diesel tradition. The stakes grew when Tesla entered the market, challenging traditional manufacturers with Silicon Valley's aggressive, well-funded approach. Peterbilt had to balance innovation with its hard-earned reputation for reliability. Instead of flashy promises, the company took a methodical path. In 2018, partnerships with Meritor and TransPower yielded 15 prototype EVs, 12 Model 579 EVs, 3 Model 520 EVs for real-world testing. The results were practical, production-ready trucks. Model 579 EV, 200-mile range, 350 kilowatt DC charging, 80% in about 90 minutes, ideal for regional haul and drayage. Model 520 EV, optimized for refuge collection, servicing 1,100 bins per charge with regenerative braking. Model 220 EV, a medium-duty solution for urban delivery. Commercial adoption grew steadily, 16 EVs delivered in 2020, 36 by Q1 2021, with major clients like Einride, 150-unit order, and Honda validating the technology. This wasn't greenwashing, it was about lowering costs through efficiency. Peterbilt integrated Packard's e-powertrain for consistency and backed it with charging infrastructure support from site assessments to maintenance. Meanwhile, autonomous trials with Aurora tested real-world self-driving applications. The SuperTruck 3 program continues advancing battery and powertrain innovation, but Peterbilt's core achievement was proving progress didn't require abandoning its legacy. By merging reliability with cutting-edge tech, the company redefined itself for a new era. Peterbilt's commitment to craftsmanship has left an indelible mark on American culture. The sight of its gleaming chrome on highways, the rumble of a Packard MX engine, and the iconic red oval emblem symbolize more than a brand. They reflect values of excellence, durability, and pride in workmanship. From the first military Model 364s in 1941
Project
to
Ultimate
750,000 truck built in Denton in 2023,
Real
Peterbilt's
V3,
milestones showcase steady growth without
oh
sacrificing
look,
quality.
I want to try
These
before I buy
aren't
it.
just production numbers. They prove T.A. Peterman's vision cut scale while staying true to its roots.
Already bought it.
Today, Peterbilt holds 14.9% of America's Class 8 market, backed by over 400 dealers. This success stems from prioritizing customer needs over short-term gains. Innovations like the Smart Link fleet management platform and sustainability efforts, recognized by the 2024 Environment Plus Energy Leader Award, highlight their forward-thinking approach. Beyond industry impact, Peterbilt shapes culture. Hollywood chose a Peterbilt for Joule and Optimus Prime in Transformers because its trucks embody the quintessential American rig. The Model 359 defined owner-operator culture in the 1970s, while the Model 379 became Peterbilt's bestseller, dominating for 2 decades. The 2024 Model 589 continues this legacy, blending classic aesthetics with modern aerodynamics and safety. Just as Al Peterman innovated with surplus trucks in 1939, today's Peterbilt pioneers electric powertrains and autonomous systems. Peterbilt fosters an emotional connection competitors can't match. Vintage models draw crowds at truck shows, and restorations preserve trucking history. The brand stands for quality beyond industry lines, embodying an American ethos of solving problems through engineering. More than a business success, Peterbilt represents a cultural icon built on doing things right, no matter the cost. Today's engineers continue that tradition across global markets, from electric powertrains to autonomous systems. From Alfred Peterman's frustration with broken-down logging trucks to today's electric and autonomous vehicles, Peterbilt represents something uniquely American, the belief that any problem can be solved with better engineering. What does the Peterbilt name really mean today? It means the same thing that it meant when that first Model 260 rolled off the Oakland assembly line in 1939. Quality matters more than shortcuts, and customer needs drive innovation. The red oval emblem still means what it meant in 1953, a commitment to building trucks that work harder, last longer, and command respect on any road. With over 750,000 trucks produced in Denton alone, Peterbilt's impact on American transportation is undeniable. Today's engineers stand on Peterman's shoulders, ensuring every Peterbilt continues solving real-world challenges for the drivers who depend on them.
The year is 1965. The American highway is an arena of high RPM noise. Detroit diesels are screaming at the red line, and the twin-stick transmission is the undisputed king of the road. But in a struggling factory in Hagerstown, Maryland, a quiet heresy was taking shape. An engineering gamble that would rewrite the rulebook of heavy haulage in ways no veteran driver could have predicted. While the world demanded speed, a rogue team of engineers bet everything on a silent revolution. The Maximo,
That damn truck, I think,
motivated
was
by
riding
the
a
threat of
wheelie.
bankruptcy and armed with a secret fleet of Learjets known as Bulldog Airlines, this underdog engine snapped axles, defied gravity on the grapevine, and saved the Bulldog from extinction. But to do it, they had to declare war on the gear shift and prove that noise isn't power. By 1965, Mack Trucks was fighting a war on two fronts. Inside the boardroom, the company was a lone bulldog under siege. While the public saw a legacy brand, corporate raiders saw a bleeding giant ripe for the picking. Rivals like White Motor Company and Chrysler were circling, looking to swallow the independent manufacturer whole. Mack wasn't just fighting for market share, it was fighting for its life. On the highways, the situation was just as grim. The industry was in the middle of a horsepower revolution, and Mack was getting left in the dust. Drivers were flocking to the high-revving two-stroke screamers from Detroit Diesel and the polished muscle of Caterpillar. Those engines made power through speed. To get a heavy load moving, you had to wind them up to 2100 RPM, or let that Detroit scream all the way to 2350 RPM and keep them there. You were shifting gears constantly just to keep the needle in the sweet spot. A Mack Thermodyne, by comparison, was reliable and sturdy, but painfully slow. It was a tractor engine in a world that wanted drag racers. Then came Zenon C.R. Hansen. He wasn't a corporate caretaker. He was a true believer who ran the company with a literal bulldog statue on his desk and a refusal to lose. Hansen knew Mack couldn't win by copying Cat or Detroit. If they built a high RPM screamer, they'd just be a cheap imitation. He needed a secret weapon. He called it Bulldog Airlines, a private fleet of Learjets and helicopters to shuttle engineers and blueprints between Allentown and the plant in Hagerstown. This kept the project off the books and away from corporate red tape. He put the task on Chief Engineer Walter May and the Hagerstown lead, Wynton Pellisoni. May and Pellisoni ran a skunkworks operation that threw out the rulebook of diesel engineering. They didn't want an engine that spun faster. They wanted the Ent 675, an engine that worked harder as it slowed down. They called it constant horsepower. In 1965, that sounded like a lie. In a standard engine, horsepower and RPM are married. When your engine speed drops, your power drops with it. That's why trucks crawl on hills. The engine loses its mechanical edge the slower it turns. May wanted to break that marriage. He wanted an engine that would crank out massive torque as the RPMs dropped, keeping the horsepower line flat even as the engine neared a stall. The wall they hit was airflow. A diesel is just a big air pump. To burn more fuel and create torque at low speeds, you have to jam more air into the cylinders. But turbos need exhaust gas to spin. At low RPM, there's no exhaust flow. The turbo stays lazy, the engine starves for air, and you end up with a stalled truck and a cloud of choking black soot. The Hagerstown team had to force feed the block while it was barely turning. They developed a specialized fuel system and the tip turbine intercooler fan. This was a small, air-driven turbine that spun a cooling fan with beds of fire. Even in the turbo, to catch a breeze. It was built for one reason: to cheat the physics of low-speed combustion. Hansen bet everything on this. In 1967, he even merged with Signal Oil just to get the cash to keep the raiders away while the engineers worked. There was no plan B. When they finally put the prototype, the Maxidine, on the dyno, the results were staggering. The power curve didn't look like a mountain. It looked like a flat table. The engine put out a constant 237 horsepower all the way from 1200 up to 2100 RPM. But the torque was the real shock. Industry standard torque rise was about 15%. The Maxidine saw a rise of over 50%, hitting 906 pound-feet at just 1200 RPM. It produced a massive surge of twisting force right where every other engine on Earth would have coughed and died. It behaved like a steam locomotive. The constant horsepower theory worked. They had built the first high-torque rise diesel in history. But as the engineers celebrated, a new problem hit them. The Maxidine put out so much raw, low-end twisting force that it was a danger to the truck. The transmissions, drive shafts, and axles in the warehouse were built for the old, weaker engines. If a driver dropped the hammer on a Maxidine through a standard box, the engine wouldn't stall. It would shear the teeth off the gears or snap the axle shafts like toothpicks. They had built a monster, and they didn't have a cage strong enough to hold it. The engine was essentially a wrecking ball. When Mack bolted those first Maxidines into test chassis, they hit a wall that physics had promised, but their budgets hadn't. That massive low-end torque didn't just move the load, it hunted for the weakest link in the drivetrain and snapped it. In 1966, standard transmissions and axles were built for horsepower, not grunt. They were designed to handle the high RPM spin of a Detroit or a Cummins, where the stress is spread out over thousands of rotations. The Maxidine, though, delivered a crushing, twisting force just above idle. Routine test drives turned into salvage ops. The torque twisted standard drive shafts until they looked like licorice, and sheared axle half shafts like they were made of glass. The engine was ready to work, but it was physically tearing the truck to pieces. To save the project, Mack stopped building just an engine and started building a philosophy: the integrated powertrain.
It's cleaned out.
They couldn't trust outside suppliers like Spicer or Fuller to build a box that could survive the Maxidine. They had to build it themselves. The answer
Tickles.
was the
You get your phone cleaned out.
Maxitorque transmission, later refined into
Storage.
the TRL 1076.
Oh, no.
This was the industry's first triple countershaft design.
Ah.
Instead of shoving all that twisting force through one main shaft, the Maxitorque split the load across three. It's the mechanical equivalent of having three men lift a heavy beam instead of one. It made the gearbox shorter, lighter,
Now
and indestructible.
on your
This
Google,
move toward building everything in-house created a
you can,
legendary
if you're doing
status.
photos, you can say
Chief
like the
engineer Walter
original,
May set
like,
a strict
and it'll
hierarchy.
put it into
If
a
truck had
format, and
Mack
it'll store
engine, Mack
unlimited.
transmission, and Mack
As
axles,
long as you don't
it was
tell it
pedigree
original,
and got the gold bulldog
it
on
is
the
stored
hook.
in a good enough
If it used
copy
vendor
that, you
parts,
know,
it
you're
got
not
the
going to
chrome
notice any
But while the
diminish
gold
to it.
bulldog looked good, the transmission itself started a war
And
with
it'll
the
hold
guys Mack needed
those
most.
kind of photos for free.
Because the Maxidine stayed
It just
in power
automatically
from
does it.
1200 to 2100 RPM, it didn't need a dozen gears. Mack simplified the whole thing down to a single stick with just 5 speeds. Engineering-wise, it was a masterpiece. Culturally, it was an insult. You have to remember the hierarchy of the road back then. Shifting was the ultimate skill check. The Knights of the Road took pride in mastering twin-stick setups, or the new 13-speed splitter, a gymnastics routine where you'd steer with your knees while rolling 2 levers at once to keep the engine singing in a tiny 300 RPM window. Then Mack hands them a 5-speed. It looked like something out of a station wagon. Mack called it a 5-speed, but that deep, low-hole gear gave you enough reduction to crawl 80,000 pounds out of a soft job site without smoking the clutch. To a veteran driver, the Maxidine wasn't progress, it was a slap in the face. It implied the job was so easy a child could do it. They started calling it a dog, not because of the mascot, but because they thought it was a neutered truck for lazy steering wheel holders. The problem wasn't just ego, it was muscle memory. Early tests were a disaster because drivers couldn't stop themselves from shifting. For decades, they'd been trained that when an engine tone dropped, the truck was about to stall. The sound of a bogging engine triggered a panic response to downshift immediately. But the Maxidine thrived in the low. When it hit a hill and the RPMs fell, the fuel pump shoved more fuel into the cylinders and the torque climbed. The truck would dig in and pull harder the slower it went, but the drivers wouldn't let it. As soon as the needle hit 1500, they'd panic and drop a gear. That sent the RPMs screaming toward the red line, right out of the torque wheel, killing their momentum and their fuel mileage. The machine wanted to work, but the human kept getting in the way. Mack realized they couldn't just explain this, they had to mandate it. They had to deprogram a generation of men who drove by ear. It got so bad that Mack had to rivet a metal instruction plate, part number 1241, right on the dash. It was a dashboard commandment. Do not downshift until engine speed drops to 1200 RPM. It forced the driver to sit on his hands and wait while the engine grunted at a low, uncomfortable churn. They had to trust the machine wouldn't quit, even though their ears told them it was dying. They hated the silence, they hated the lack of work, and they hated that plate telling them how to drive. But while they were grumbling in the cab, the truck was doing something undeniable on the asphalt. A new legend was being forged, not by speed, but by a relentless, unbreakable will to pull. You had to go to the Tejon Pass in California, better known to truckers as the Grapevine. That 5-mile stretch of asphalt climbs at a punishing 6% grade, and by the late 1960s, it was the unofficial courtroom where horsepower disputes were settled. This is where the Maxidine had its tortoise in the hare moment. On paper, the contest was a joke. You had the industry standard, a massive Cummins NTC 335 pushing 335 horsepower, mated to a complex 13-speed box. Against it stood the Mack Ent 675, rated at a humble 237 horses with that weird 5-speed stick. In the world of heavy haulage, a 100 horsepower deficit should have been a death sentence. The Cummins driver probably looked at the gold bulldog on the Mack's hood and assumed he'd leave it in a cloud of soot before the second mile marker. But the physics of momentum tells a different story than the brochure. As the grade steepened, the Cummins did exactly what traditional diesels do. It screamed to the red line, ran out of breath, and forced a shift. Every time that driver hit the clutch, the fuel cut, the exhaust pressure dropped, and the turbo started to spin down. For that split second of shifting, the truck was just coasting against gravity. The driver was frantically working the twin sticks, hunting for a gear to keep the RPMs high enough to stay on boost. It was a sweaty, high-effort battle to stay in the narrow power band. Meanwhile, the Mack driver sat in the right lane, doing almost nothing. He put the truck in fourth at the bottom and left it there. As the grade bit in, the engine didn't choke, it dug in. The RPMs dropped, but the torque rose and the fuel flow increased automatically. The turbo stayed spooled, jamming compressed air into the cylinders. There was no pause for a shift and no loss of momentum. While the Cummins was losing 3 miles per hour with every gear split, the Mack held a steady, relentless pace. By the top of the grapevine, the weaker Mack had often passed the 335 horsepower Giant simply because it never stopped pulling. The Cummins had the peak numbers for the brochure, but the Mack had the area under the curve. It stayed in the fight, while the other guy was busy clutching. That victory proved the concept, but it didn't make the drivers like it. They still wanted the noise and the gears. But in 1973, the world forced their hand. The oil embargo hit like a hammer. Diesel went from 27 cents a gallon to over 45 cents. Liquid gold almost overnight. Suddenly, operating costs were the only metric that mattered. Fleets staring at bankruptcy started auditing their fuel logs. They noticed something Hansen and May hadn't even led with. The Maxidine was accidentally a fuel-sipping miracle. The math was simple. A typical Detroit or Cummins struggled to get 4.5 miles per gallon. The Maxidine was hitting 6.1. Why? Physics. Friction increases with the square of engine speed. An engine screaming at 2100 RPM is fighting itself, wasting energy just to keep the pistons moving. By lugging at 1200 RPM, the Mack cut those internal friction losses to the bone. Plus, by cutting out all that shifting, the truck wasted less energy getting back up to speed. In a low-margin industry, that gap was the difference between staying in business and folding. Then came the final nail. The 55-mile-an-hour speed limit hit in 1974. For Hare engines, this was a disaster. At 55, their gearing put them in a dead zone around 1650 RPM. Too slow for boost, too fast for downshift. They were constantly fighting the truck. The Maxidine, however, was built for exactly that range. It sat right on its torque peak at 55. The government had effectively mandated the Maxidine as the national standard. The transmission wars ended right there. It didn't matter if a driver's ego was bruised by a 5-speed stick. The guys signing the paychecks couldn't afford the ego anymore. Mack couldn't build them fast enough. Competitors who had laughed at the low RPM experiment were suddenly tearing down Mack engines to see how they worked. But engineering is a game of trade-offs. You don't get something for nothing. The Maxidine had mastered going up the mountain, but in their focus on pulling power and fuel economy, the engineers overlooked one thing. What goes up must come down. The very thing that made the engine efficient, low friction and low RPMs, meant it offered zero resistance when gravity took over. Standard engines used high RPM friction to help slow the truck down. The Maxidine just wanted to roll. The silence under the hood was about to turn from a selling point into a nightmare, because a quiet engine is the last thing you want when you've got 40 tons of cargo pushing you toward a cliff. Gravity doesn't care about your fuel economy, and it certainly doesn't care about your profit margins. While the Maxidine was printing money for fleet owners on the flat, it was creating a nightmare for drivers staring down a 6% grade. In a traditional rig, you relied on the screaming resistance of the engine to hold back 80,000 pounds of steel. High RPMs create friction and back pressure. It's a natural anchor. But the Maxidine was designed to live in a lazy, quiet rumble. When a driver crested a pass and lifted his foot, he was met with frightening silence. The low-friction engine offered almost zero resistance. This was the Maxidine trap. Because of the wide gear spacing, if you crested a hill too fast, you couldn't slow down enough to grab a lower gear. You were stuck in high gear with a freewheeling engine, forced to smoke your wheel brakes just to stay on the road. Mack knew they'd solved the efficiency puzzle, but accidentally broke the safety equation. They rushed out their own engine brake, the Dynatard. The industry standard was the Jake brake, a brutal system that turned the engine into a massive air compression, putting out 240 braking horsepower. But Jakes worked best at high RPM, exactly where the Maxidine didn't want to be. The Dynatard was a hydraulic setup built into the valve train. On paper, it was clever. In the real world, it was weak. It relied on engine oil, so when the oil got hot and thin on a long grade, the braking faded. It put out maybe 150 horsepower, barely half of a Jake. Drivers immediately dubbed it the Dyno Retard. It wasn't just a joke, it was a matter of survival. This resentment sparked a culture war between the shop and the cab. To keep things clean and efficient, the Maxidine used a puff limiter. This was a little air cylinder on the fuel pump that blocked the fuel rack from opening until the turbo built enough boost. It prevented unburned fuel from exiting the stack as black smoke. It kept the engine clean, efficient, and EPA friendly. But drivers didn't want clean. They wanted throttle response. The limiter's job was to physically pin the fuel rack, stopping it from sliding wide open until the turbo caught up. But the outlaw drivers figured out how to bypass that connection. They ran a line straight from the wet tank, the primary air reservoir, forcing the rack wide open with a constant 100-pound hit of unregulated pressure. This tricked the engine into thinking it had full boost the second they touched the pedal. The result? A thick black plume of soot every time they gear jammed the throttle. Rolling coal wasn't just for show, it was rebellion. It was the driver reclaiming control from the engineers in Allentown. This sabotage came at a price. By killing the puff limiter and winding the Maxidine out to 2100 RPM to make it sound like an old Detroit, drivers were cooked. They'd bury the throttle and watch the pyrometer needle climb past 1200 degrees, cooking the oil and the metal. The high heat and soot loads blew up turbos at an alarming rate. Managers blamed the engine. Drivers blamed the design. It was a mechanical stalemate. The weirdest part? To the rest of the world, Mack was the hero. In 1978, the movie Convoy turned the Mack RS700L into a global icon. The rubber duck drove a sinister, blacked-out Mack that became the face of the outlaw trucker. But if you listen to that movie, you're hearing a lie. The real Maxidine, specifically the N676, made a high-pitched pneumatic whine that didn't sound tough enough for Hollywood. It had a signature tea kettle whistle that signaled to everyone at the truck stop exactly what was under your hood. It hummed, didn't roar. The director made a choice that still bugs purists. They dubbed the sound of a screaming Detroit 8B71 over the Mack footage. The public fell in love with the look of the Bulldog, but they were listening to the sound of the very technology Mack was trying to kill off. Everyone wanted the look, but nobody was ready to let go of the noise and the fury. The industry was in a Wild West phase of engineering, and the chaos couldn't last forever. By the 1980s, the Wild West era of diesel had to grow up. The Maxidine had proven that low-end grunt was the future, but the hardware needed to get cleaner and tougher. Mack's engineers looked at the plumbing on the early models, specifically that tip turbine system. It was a genius piece of work, but it was complex, expensive, and used active air bleeds that were a pain to maintain. The fix they found didn't just refine the engine, it changed the way American trucks looked forever. The innovation was the Chassis Mountain Charged Air Cooler, CMCAC, or what most of us just call the air-to-air intercooler. When a turbo compresses air, that air gets hot, up to 325 degrees. Hot air is thin and carries less oxygen. Instead of using complex fans or radiator water to cool it down, Mack went passive. They slapped a massive heat exchanger right in front of the radiator to catch the wind hitting the nose of the truck. This dropped intake temps from a scorching 325 degrees down to a cool 110. The change had a physical side effect. To
I'm
fit
going
that
the wrong
massive
way.
cooler, the front grille on the R model and the Superliner had to be raised and squared off. It gave the trucks that tall, muscular snout that every Mack fan knows by heart. Under the hood, this cooler meant the engine burned fuel cleaner and extracted more power without melting pistons. They combined this with the new 4-valve cylinder head, extracting more power from every drop of diesel. Mack rebranded this evolution the Econodyne. It kept the 60s grunt, but added 80s efficiency. The Econodyne ended the debate. For 20 years, Cummins and Detroit had scoffed at the low RPM life, but by the mid-70s, they couldn't ignore the fuel math anymore. In a move that proved that Zenon Hansen was right all along, Cummins effectively surrendered in 1974. They launched the Formula Series, which did exactly what Mack had done. It choked the governor down from 2100 to 1900 RPM to force fuel economy. The industry had been dragged, kicking and screaming, into Mack's world. The days of shifting at 2300 RPM were dead. But as Mack went global, they found out the Maxidyne wasn't a magic key for every door. Over in the UK, the constant horsepower philosophy hit a wall. American highways are built for locking it into high gear and letting the torque do the work. The UK is a mess of tight roads, roundabouts, and constant stops. British drivers hated the 5-speed box. To hit a roundabout, you need precision. With those wide gear gaps, drivers were always in no man's land. Too fast for third, too slow for fourth. The engine wanted the lug, but the traffic required a dance. The very thing that made the truck a legend in the States made it a headache in Europe. But down in the southern hemisphere, it was a different story. The Australian Outback was custom built for the Maxidyne. The roads weren't just long, they were endless, unpaved, and brutal. We're talking road trains, one tractor pulling 4 or 5 trailers through soft dirt and sand. In the Outback, momentum is your only friend. If you have to shift while pulling 100 tons through soft sand, you lose your pull and the truck sinks. The Maxidyne's ability to lug down to 1000 RPM without stalling meant Aussie drivers could hold a gear through a soft patch where a Cummins-powered rig would have bogged down. The proof came in 1988. A driver named Plugger Bowden set a world record with a Mack Superliner called the Mack 88. He hauled a staggering 1.1 million pounds, a road train 1,440 feet long through the red dust. The Maxidyne principle worked even when you were pulling a small town's worth of weight. This led to the Mack Titan, a beast built specifically for heavy haulage. It became the backbone of Australian mining and cattle, operating hundreds of miles from the nearest wrench. Mack was at the top of the mountain. They had forced the competition to copy them, conquered the harshest dirt on earth, and built a reputation for being unbreakable. But in the corporate world, that kind of independent success makes you a target. The gold bulldog was shining, but keeping that shine was about to cost a lot more than just engineering hours. Corporate dominance usually comes with a price. By the late 1970s, Mack was willing to pay it with the blood of its own family. While the engineers were perfecting the low RPM life, the boardroom entered a phase of calculated ruthlessness. This wasn't just about beating rivals like White or International anymore. It was about cannibalizing their own assets to build a new flagship. The victim was the Brockway Motor Company. Mack had owned this New York-based builder for years, letting them produce distinct, rugged trucks known as Huskies. Brockway had a reputation for heavy-duty resilience, and more importantly to Mack's suits, they had a square-jawed, flat radiator look that commanded respect. Mack needed a new high-end model and didn't want to spend years in R&D designing a cooling package from scratch. In a move that still leaves a bitter taste in the mouths of restorers, Mack liquidated Brockway in 1977. They shuttered the factory, fired the men, and raided the parts bin. The flat radiator and hood of the dead Brockway were grafted onto a Mack chassis. The result? The Mack Superliner. It became an instant legend, but that aggressive square-nosed look was born from the ashes of a company Mack deliberately suffocated. Before the accountants completely strangled the shop, the Maxidyne concept had one final thunderous peak, the E9 V8. If the early 6 cylinders were about efficiency, the E9 was about absolute, unadulterated violence. This was the constant horsepower philosophy pushed to the edge. A massive 16-liter monster, the E9 wasn't for hauling groceries. It was for the loggers and heavy haulers moving 200,000 pounds up a mountain. In specific tunes, the E9 eventually climbed to 1,000 horsepower, science fiction of the 1980s. But it hit a physical wall, heat. Generating that much low-end grunt created a thermal load that could turn a cab into an oven. It was the dinosaur that signaled the end of the age of giants. Magnificent, and too hot to survive that mistake. In the year 2000, the era officially ended. For decades, Mack had been a sovereign state. They built their own iron, their own gears, and their own axles. But in a global economy, being a loner is financial suicide. Volvo immediately acquired Mack and shipped it to Netherlands. The unique engineering Xenon Hansen fought for began to dissolve into global platforms. The Maxidine was replaced by the MP series engine. While a Mack MP8 and a Volvo D13 shared the same block, Mack engineers fought to keep the soul alive in the software. They used specific VMAC programming and aggressive cams to mimic the torque rise of the old Maxidine. They made sure the truck still pulled like a bulldog, even if the heart was shared with a Viking. But for the old school mechanics, the arrival of the VMAC electronics meant the end of the screwdriver tune. You couldn't just walk up to the pump and turn up the fuel anymore. For the real aficionados, the signature of this era is the sound of silence. If you're at a truck stop today and hear a high-pitched whirring coming from a parked Mack for 90 seconds after the key is pulled, you're hearing the Centramax. It's a centrifugal oil filter spinning at 5,000 RPM, squeezing soot into a dense cake. It's inside baseball.
Driver, you're getting close to your delivery. Slow it down and get ready to enter the facility. Check in with receiving when you arrive and let us know once you're backed in and ready to unload. Dispatch out.
Gold meant all Mack, engine, trans, and axles. It was a warning to other drivers that this was a cohesive, integrated machine. Under new ownership, the Gold Bulldog slowly turned from a technical standard into a marketing trim level. As trucks became more computerized and harder to fix with a wrench, a resistance movement formed. Veteran drivers looked at the plastic and sensors and said, "No thanks." They started hunting for old iron. This sparked the rise of the glider kit underground. Operators used a legal loophole to pair a brand new chassis with a mechanical E6 or pre-emissions E7, tuned to that legendary 427 horsepower. They wanted to avoid the EGR and DPF systems that were choking modern rigs. It was here that the spirit of the original Maxidine found its last sanctuary, a mechanical bunker for guys who refused to let go. But holding on to the past is a fighting retreat. The era of the mechanical miracle is closing, replaced by the era of the algorithm. Ultimately, the Maxidine proved that in the long war between tradition and physics, physics always wins. Xenon Hansen's gamble didn't just save a company, it predicted the future of the entire industry. The downspeeding engines powering modern Volvo and Daimler fleets today are the direct descendants of that Hagerstown garage project. It turns out Walter May was 50 years ahead of his time. He showed the world that a diesel engine is designed for work, not for noise. The era of the screamer is over, but the legend of the high-torque rise engine lives on every time a modern rig pulls a heavy grade without breaking a sweat. It's a legacy of efficiency, grit, and the stubborn refusal to do things the way they've always been done. If you ever wrestled with a Dynatard on a steep grade or spent your nights listening to a tip turbine whine, leave a comment below. We want to hear your real-world war stories from the cab. And if you want more real talk on the machines that built this country, hit that subscribe button.
They power our lives. From cars to lawnmowers, from ships to steam trains. They've transformed our world and taken us to the moon. Now, engines on Modern Marvels. It's no accident that the root word of engine is ingenious. For 3 centuries, these ingenious designs have been the ultimate expression of man's desire for technical excellence. And through many generations of technological progress, they've had a profound effect on the way people travel and work. Steam engines replaced the horse. Electric motors and gasoline engines replaced the steam engine. Then, the jet engine and the rocket engine took things to a higher level. And now, microtechnology engines are proving that less is more. This march through the centuries began when the steam engine ushered in the Industrial Revolution. It freed mankind from total dependence on primary sources of power, like wind, water, and muscle. Steam
All right,
engines will
driver,
be used
that
to
wraps
power
up the
factory
route.
machinery,
All stops have been
trains,
completed and
ships,
confirmed.
tractors,
Good
and
work out there.
automobiles.
Take a breather,
Before
stay
steam,
safe,
mostly we used
and stand
animals,
by for the next load.
as our mode of
Dispatch out.
transportation. When steam came along, of course, we could move more material faster and more reliably than we could, of course, with animals. And so that was a big transformation. People became less tied to being in small cities. They could live out on the farm and still be connected, if you will, to the cities.
In a steam piston engine, steam enters one end of a cylinder and pushes a piston back. Then it enters the other end, pushing it the other way. The steam comes from a boiler, a metal water container that is heated, usually by burning fuels like wood, coal, oil, or natural gas. A steam turbine engine is like a windmill, except that its blades are propelled by hot steam under high pressure instead of wind. To this day, steam turbines are widely used. In fact, they are used to generate most of our electricity. The Greek scientist Hero of Alexandria built the world's first steam engine about 2,000 years ago. It was basically